Chapter 1. The 70,000-Year Prison. Imagine standing in the quiet darkness of the southern hemisphere, peering up at a tiny, faint red dot in the constellation of Centaurus. This is Proxima Centauri, a small red dwarf star that, for all its dimness, holds a singular title. It is our closest stellar neighbor in the entire galaxy. On a cosmic star chart, this looks like a short hop, a mere stone's throw in the grand ocean of the Milky Way. But for humanity, this neighbor is locked behind a 25 trillion-mile gap, a number so vast it breaks the human intuition for scale. To write that figure out, you would need to place 12 zeros after the number 25. If the entirety of our solar system was shrunk down to the size of a single quarter, Proxima Centauri would still be 300 meters away. This is the starting point for every interstellar mission planner, a blunt, terrifying confrontation with the sheer cold size of space. We often talk about the speed of light as the ultimate velocity, the fastest thing in the known universe, racing at 186,000 miles per second. At that incomprehensible speed, a photon could circle the Earth's equator 7 times in the time it takes you to blink. Yet, even this universal speedster is humbled by the distance to Proxima. A beam of light leaving that star right now won't reach your eyes for 4 years and 3 months. If we sent a radio message today to any potential civilization orbiting that star, a child born this morning would be learning to read by the time we received a simple hello in return. But we aren't made of light, we are made of heavy matter, and our current reality of travel is not measured in years, but in millennia. To understand the true scale of our cosmic prison, we have to look at our fastest champion, Voyager 1. Launched in 1977, Voyager 1 has been screaming through the void for nearly half a century and has become the most distant human-made object in history. It is currently moving at a staggering 38,000 miles per hour relative to our Sun. To put that in perspective, a commercial airliner cruises at 600 miles per hour, and a bullet leaves a rifle at 2,000 miles per hour. Voyager 1 is traveling 19 times faster than a speeding bullet. It covers 333 million miles every single year, a speed that could take you to the moon in less than 7 hours. But when you plug that bullet-like velocity into the equation for reaching our nearest neighbor, the result is devastating. At its current speed, it would take Voyager 1 approximately 70,000 years to reach Proxima Centauri. To grasp how long that is, consider that the first cave paintings in Europe were made only 40,000 years ago. Agriculture was invented a mere 12,000 years ago, and the very concept of writing is only 5,000 years old. The entire recorded history of the human species would fit inside 1/4 of a single Voyager trip to the nearest star. If Voyager were actually headed there, humanity as we know it today would likely be unrecognizable or perhaps extinct by the time the probe finally arrived. And Proxima is the easy target. If you wanted to visit Sirius, the brightest star in our sky, you are looking at a 150,000-year journey. If you aimed for Betelgeuse, the red supergiant in Orion, a Voyager-class probe wouldn't arrive until our own Sun has exhausted its fuel and begun to swell into a red giant, consuming the Earth entirely. The engineering reality we face is not just difficult, it is brutal. We cannot simply inch our way to the stars by building slightly faster versions of the engines we have today. Every factor of 10 improvement in rocket speed only shaves a single zero off a timeline that is already unreachable. The reason for this failure is a mathematical monster known as the tyranny of the rocket equation. Since the 1950s, engineers have known that chemical rockets, the kind that powered the Saturn V and the Space Shuttle, work on a principle of diminishing returns. To move a spacecraft, you must burn fuel to create thrust, but that fuel has mass. Therefore, you need more fuel to push the weight of the fuel you're already carrying. This creates an exponential spiral where the mass of the rocket grows faster than the energy it can provide. Take the Saturn V rocket as an example. To push a tiny capsule containing 3 men 250,000 miles to the Moon, that monster of an engine had to burn 3,000 tons of fuel in its first stage alone, 3 million kilograms of kerosene and liquid oxygen consumed in just 2.5 minutes. Now try to scale that up to Proxima Centauri, which is 100 million times farther away than the Moon. If you tried to reach the nearest star in a single human lifetime using chemical rockets, you would need more fuel than exists on the entire planet Earth. This is not an exaggeration. Even if you harvested every hydrocarbon from the atmospheres of Jupiter and Saturn and stripped every organic molecule from every asteroid and comet in the solar system, the math still fails. The rocket equation simply does not care how much fuel you have. It cares about the ratio between fuel mass and payload mass, and for interstellar travel, that ratio explodes into impossible, ridiculous values. Engineers have spent 70 years sketching desperate alternatives on napkins and supercomputers. We've dreamed of nuclear pulse propulsion, detonating atomic bombs behind a lead shield to ride the shockwave. We've imagined antimatter engines that convert 100% of their mass into raw energy through annihilation. We've even proposed breakthrough starshot using ground-based laser arrays to push sails the size of a postage stamp to 20% the speed of light. Each of these designs claws a few more percentage points of velocity, but none of them can break the real ceiling. The real ceiling isn't a lack of fuel or a lack of power. It is a fundamental law of nature, woven into the very geometry of the universe. In 1905, Albert Einstein revealed that the speed of light is the universe's ultimate speed limit. It is a wall that mass simply cannot climb. As an object moves faster, its effective mass increases. The closer you get to light speed, the more energy you need to gain the next mile per hour. To actually reach light speed, an object would need infinite energy, which simply does not exist. We are, for all intents and purposes, trapped in a local bubble of space, separated from the rest of the galaxy by distances that our current physics says are impassable. We are passengers on a planet that will one day become uninhabitable, looking at Earth 2.0 candidates like Proxima Centauri b, knowing they are reachable in theory but impossible in practice. But what if the problem isn't the rocket? What if the problem is how we think about moving altogether? If we cannot move through space faster than light, is there a way to make space itself do the moving? Deep within the very same equations Einstein used to build this prison, a young physicist found a hidden door that had been locked for nearly a century. And that door is where our story truly begins. Chapter 2. The Cosmic Firewall, the Light Speed Mystery. If you open any modern physics textbook, you will find a number stated with absolute unwavering certainty. 299,792,458 meters per second. This is the speed of light in a vacuum. It is the universal constant that dictates how fast your internet travels, how the sun warms your face, and how the very fabric of time and space is woven together. But here is the terrifying secret hiding in the heart of modern science. Humanity has never actually measured the speed of light. This sounds like a conspiracy theory, but it is a profound truth acknowledged by every major scientific institution on Earth. In 1983, the international scientific community made a radical decision. They stopped trying to measure the speed of light and instead defined it into existence. They decreed that the speed of light is exactly that number, not because they found it in a lab, but because they needed a fixed foundation to keep the universe's bookkeeping consistent. This created a bootstrap paradox where our entire understanding of distance is built on a constant that we've essentially voted into reality. To understand why this paradox exists, you have to look at the one-way speed of light problem. We can easily measure the round-trip speed of light, bouncing a laser off a mirror and timing how long it takes to return. But to measure light in a single direction, from point A to point B, you would need two clocks, one at each end, that are perfectly synchronized. The catch? According to Einstein, the only way to synchronize those clocks is to know the speed of light beforehand. We are stuck in a logical circle. We have decreed light moves at the same speed in all directions to make our math work, but for all we know, light could move at half that speed toward you and instantaneously away from you. We wouldn't know the difference because our rulers and clocks are all defined by the very thing we are trying to measure. This is the first layer of the cosmic firewall. We think we understand the speed of light, but we've actually just built a conceptual prison around it. For over 2 centuries, brilliant minds tried to pin this number down. In the 1670s, Alcubierre watched the moons of Jupiter disappear and reappear, realizing that light wasn't instantaneous but had a finite travel time. In 1849, Armand Fizeau used a rapidly spinning gear wheel to catch light beams between its teeth. Each experimenter got closer and closer, but they eventually hit a wall that wasn't technological, it was geometric. This brings us to the rule. In 1905, a 26-year-old patent clerk named Albert Einstein published a paper that demolished over 2 centuries of physics. He revealed that the speed of light isn't just a fast speed, it is a structural feature of reality itself. Einstein showed that as an object with mass approaches the speed of light, its effective mass begins to increase. This isn't just a mathematical trick, it's a physical transformation. Imagine you are on a spacecraft trying to reach that 186,000 mile per second limit. As you push your engines harder, the energy you pump into the ship doesn't just make you go faster, it starts turning into added mass. By the time you reach 99% of the speed of light, your ship's mass has grown by a factor of 7. At 99.9%, your mass has increased by a factor of 22. To gain that last fraction of a percent, you would need to consume more energy than is produced by entire stars burning for millions of years. To actually hit 100% of the speed of light, your mass would become infinite, requiring infinite energy to move, a quantity that simply does not exist in our universe. This is the unbreakable wall. It's why every interstellar mission ever sketched on paper, from nuclear bombs to antimatter drives, eventually fails. You aren't just fighting your engines, you are fighting the geometry of the universe. The speed of light is the maximum rate at which causality itself propagates. If you were to somehow jump past it, you wouldn't just be moving fast, you would be violating the ordering of time. From the perspective of certain observers, a faster-than-light signal would arrive at its destination before it was even sent. You could receive a reply to a question you hadn't even thought of yet. The universe guards its speed limit with such ferocity because if the limit breaks, logic itself dissolves into chaos. But even as Einstein was building this prison, he accidentally left a hidden door unlocked. This is the loophole. While Einstein's equations are absolute about objects moving through space, they say something very different about the movement of space itself. Space is not an empty nothingness. It is a dynamic, flexible medium that can be stretched, compressed, and curved by mass and energy. And crucially, there is no speed limit on how fast space can move. We know this is true because we can see it happening right now in the furthest reaches of the cosmos. The universe is expanding, and it isn't just expanding slowly. Astronomers have discovered that distant galaxies, those roughly 14 billion light-years away, are receding from us at velocities that exceed the speed of light. They aren't breaking the law because they aren't actually moving through their local patch of space. Instead, the space between us and them is stretching. Imagine two ants sitting perfectly still on a massive rubber sheet. If you grab the edges of that sheet and pull with incredible force, the ants will separate from each other at superluminal speeds. The ants aren't running, they are just riding the expansion of the rubber. This is called metric expansion, and it is an observationally confirmed fact of our universe. We regularly photograph galaxies that have already crossed the cosmological horizon, meaning their light will never reach us again because the space between us is growing faster than light can cross it. This is the ultimate distinction that every warp drive scientist relies on. Nothing can move through the fabric of the universe faster than light, but the fabric itself can go as fast as it wants. For decades, this was treated as a curiosity of the deep cosmos, a trick only the Big Bang or dark energy could perform. Mission planners stared at this loophole and wondered, if space can carry entire galaxies apart at faster than light speeds, could we engineer space to carry a spacecraft? Could we create a local region of spacetime that compresses in front of a ship and expands behind it, letting the ship ride the resulting wave like a surfer? Inside such a pocket, your clock would run normally. You would feel no g-forces, no matter how fast you accelerated, because you wouldn't be moving through space. You'd be sitting in a flat bubble of space that is being transported by the geometry around it. You wouldn't gain infinite mass, and you wouldn't violate the laws of relativity, because locally you are staying still. You've effectively relocated the speed limit rather than breaking it. The idea sounded like a fever dream until 1994, when a young Mexican physicist decided to treat the Star Trek warp drive as a serious homework problem. He sat down with Einstein's field equations and asked them a question that changed the trajectory of human history. What shape would space have to be for this to work? When the equations answered him, the modern era of warp drive research didn't just begin, it exploded into a valid mathematical reality. But, as we are about to see, the price for opening that hidden door was a requirement so impossible it would take humanity another 30 years just to figure out a way to pay it. Chapter 3. Alcubierre, Star Trek. Homework. In the spring of 1994, the world of theoretical physics was shaken by an 8-page paper that began not with a laboratory breakthrough, but with a piece of science fiction. At the time, Miguel Alcubierre was a 28-year-old Mexican physicist pursuing postdoctoral research at the University of Wales. Like millions of others, Alcubierre was a fan of Star Trek, a show where the crew of the Enterprise hopped between star systems as casually as we cross city limits. But while the rest of the world saw warp drive as a convenient plot device to avoid 70,000-year travel times, Alcubierre saw a mathematical challenge. He decided to treat the fictional propulsion system as a serious homework problem, asking himself, what shape would space-time actually have to take for this to be real? Alcubierre's genius lay in reverse engineering the metric. In the century following Einstein's general relativity, most physicists worked in one direction. They identified a distribution of matter, like a star or a black hole, and then calculated how it warped the space around it. Alcubierre flipped the script. He started with the desired effect, a pocket of space moving faster than light, and then worked backward through Einstein's field equations to see what kind of energy would be required to create that specific geometry. When he finished his calculations and published his results in the journal Classical and Quantum Gravity, the scientific community was stunned. The math was rigorous, self-consistent, and entirely valid within the framework of general relativity. He had turned a science fiction dream into a legitimate academic solution, and in doing so he provided the first real map for the Alcubierre warp drive. To understand how Alcubierre's solution functions, you have to stop thinking of a starship as a car and start thinking of it as a surfer. As we established in Chapter 2, Einstein's speed limit strictly forbids any object from accelerating through space faster than light. However, the fabric of space itself has no such restriction. Alcubierre's design exploits this distinction by creating a warp bubble, a localized region of spacetime that carries a ship along like a passenger on a cosmic conveyor belt. The mechanics of this bubble are as violent as they are elegant. To move forward, the drive must aggressively contract space in front of the vessel while simultaneously expanding space behind it. Imagine a rubber sheet with a small circle drawn in the middle representing your ship. If you were to scrunch the rubber together in front of that circle, the distance to your destination would literally shrink. If you then pulled and stretched the rubber behind the circle, the distance to your starting point would lengthen. The circle itself hasn't moved across the surface of the rubber. Rather, the geography around the circle has shifted, translating the ship forward without it ever needing to fire a traditional thruster. This leads to the most mind-bending feature of the Alcubierre metric. The ship inside the bubble is technically stationary. The interior of the bubble, the passenger region, is a pocket of flat space-time where the laws of physics behave exactly as they do in your living room. Inside this pocket, an astronaut could sip a cup of coffee and feel absolutely no sense of motion. There are no g-forces because the ship isn't accelerating through its local space. It is simply riding a wave of geometry. You could go from a dead stop to 10 times the speed of light in a single second, and you wouldn't be crushed against the back wall. In fact, you wouldn't even feel a jolt. This is because you are sitting in a Minkowski metric, a region of perfectly normal space that is being transported by the warped shell surrounding it. This surfing mechanism also neatly sidesteps the twin paradox of special relativity. In a traditional high-speed rocket journey, time for the travelers slows down relative to those on Earth. A pilot might return from a 5-year mission to find that centuries have passed at home. But because the warp ship is stationary within its local bubble of space, time dilation does not occur. The ship's clock ticks at the exact same rate as the clock back at mission control. You could travel to Proxima Centauri, conduct your research, and return to Earth to find your friends and family have only aged the exact number of months you were gone. However, for an outside observer, the sight of a warp ship would be a violation of everything they thought they knew about reality. They would see the bubble translate through the universe at any speed the pilot chooses, twice the speed of light, 10 times, or even 100 times. Because the bubble is a feature of space rather than an object in space, it can cross the 25 trillion mile gap to our nearest star in a matter of weeks, effectively arriving at the destination long before a beam of light following the long way through normal space could ever hope to. In Alcubierre's world, you aren't outrunning light. You are taking a geometric shortcut that light simply doesn't have access to. The scientific community's reaction to Alcubierre's paper was a fascinating mix of delight and absolute horror. On one hand, he had proven that the cosmic firewall had a back door, that Star Trek-style travel was not a mathematical impossibility. He had successfully separated the concept of motion from velocity, showing that the universe is a flexible medium we could theoretically manipulate. But on the other hand, Alcubierre's equations revealed a monumental catch. The field equations of general relativity are like a balanced scale. If you want a certain curvature of space on one side, you must place a specific amount of mass and energy on the other. To create the repulsive gravity needed to expand space behind the bubble and the intense compression needed to shrink it in front, the math demanded a substance that seemed to defy the very definition of matter. Alcubierre's solution required vast quantities of exotic matter, a hypothetical substance with negative energy density. This isn't just matter that is hard to find, it is matter that falls upward and curves space-time outward rather than inward. It is the anti-gravity equivalent of a substance that hasn't been observed in bulk anywhere in the known universe. Without this exotic fuel, the warp bubble is nothing more than a beautiful mathematical ghost, a door that we know exists but for which we have no key. Moreover, Alcubierre's original 1994 design was what physicists call energy inefficient. The early calculations were so staggering that they were almost comical. To move a small, human-sized spacecraft, the original Alcubierre metric required a quantity of negative energy equivalent to the mass of the entire observable universe. You would have to take every star, every galaxy, and every atom in existence, flip them into a negative state, and wrap them around your ship just to leave the solar system. Despite these obstacles, Alcubierre's Star Trek homework changed the trajectory of human ambition forever. He moved the conversation from if we could travel faster than light to how we could afford the energy bill. He provided the foundation that every subsequent researcher, from NASA to private labs in Manhattan, would spend the next 30 years trying to optimize. The hunt for a way to reach the stars had finally moved out of the realm of fantasy and into the rigorous, cold and exciting world of engineering. But as Alcubierre himself would soon realize, opening the door to the stars was only the first step. Once you have a bubble that can travel faster than light, you have to face a new set of problems. How do you steer a ship that is moving faster than its own radio signals? And more terrifyingly, what happens to all the space dust you hit when you're moving at 10 times the speed of light? Those answers lay in the decades of refinement that followed, as physicists began the long, arduous process of shrinking the universe-sized energy bill down to something humanity might actually be able to pay. Chapter 4. The Impossible Fuel Source. If Chapter 3 gave us the map to the stars, Chapter 4 is the moment we realize we can't afford the ticket. When Miguel Alcubierre first published his warp metric in 1994, it was hailed as a mathematical masterpiece, a rare loophole in the cosmic firewall that Einstein had built a century prior. But as the initial excitement settled, the scientific community began to look closely at the bill Alcubierre's equations had presented. The math was consistent, yes, but it demanded a physical substance so bizarre, so contrary to our daily experience, that it seemed to belong more in the realm of magic than in a physics laboratory. This is the catch, the requirement for exotic matter with negative energy density. To understand why this is such a deal-breaker, we first have to understand the matter that makes up everything you have ever touched. From the coffee in your mug to the stars in the sky, all ordinary matter possesses positive energy. In the language of general relativity, positive energy is what makes the universe work. It curves space-time inward. This inward curvature is what we perceive as gravity. It is the reason planets orbit stars and why your feet stay planted on the ground. But a warp bubble is a different beast entirely. To contract space in front of a ship and expand it behind, you cannot use the attractive gravity of a star. If you placed a massive star in front of your ship, it would simply pull you into it. To create a warp effect, you need the opposite. You need a substance that curves space-time outward, creating a repulsive anti-gravity effect. This hypothetical substance is exotic matter. It is not just matter that is hard to find, it is matter that possesses negative mass. If you held a ball of exotic matter in your hand and let go, it wouldn't fall to the floor. It would fall upward, repelled by the Earth's gravity. In Alcubierre's design, this exotic matter must be arranged in a thin, glowing shell around the spacecraft. This shell acts as the structural frame for the bubble, using its repulsive energy to prevent the warped geometry from collapsing in on itself. Without this negative glue, the warp bubble isn't just unstable, it is mathematically impossible to sustain. But the catch wasn't just about the type of fuel, it was about the energy crisis regarding the amount. When Alcubierre and later researchers ran the initial numbers for how much negative energy was needed to transport a small, human-sized spacecraft, the results were, quite frankly, comical. The original math suggested that to move a ship across the galaxy you would need a quantity of exotic matter equivalent to the mass of the entire observable universe. You would essentially have to take every galaxy, every star, and every atom in existence out to the cosmic horizon, flip them into a negative state, and wrap them around your hull. The figure was so absurd that many physicists initially dismissed the paper as a mathematical curiosity with no link to reality. However, theoretical physics is a game of optimization. In 1999, a Belgian physicist named Chris van den Broek found the first major discount. He realized that in the warped world of general relativity, the external size of a bubble doesn't have to match its internal volume. He proposed a bubble that looked no larger than an atomic nucleus, a proton, on the outside, but thanks to the extreme curvature of the shell, it could contain a vast, flat interior large enough for a starship. By shrinking the mouth of the bubble that interacted with the external universe, Van den Broek slashed the energy requirement by more than 20 orders of magnitude. The bill dropped from the mass of the entire universe down to something merely the mass of the planet Jupiter. To put that in perspective, consider this. The total mass of every satellite, rocket, and rover humanity has ever launched into space since 1957 is roughly 20,000 tons. Jupiter weighs 2 trillion tons. Even with this breakthrough discount, the warp drive had moved from absolutely impossible to merely ridiculously impossible. We were still talking about harvesting an entire gas giant and converting it into a form of matter that, as far as we knew, didn't even exist. This brings us to the ultimate question that haunted mission planners for decades. Is negative energy even real? Or is it just a mathematical ghost that appears in equations but can never be touched? The answer came from a quiet laboratory in the Netherlands, decades before Alcubierre ever saw an episode of Star Trek. In 1948, Hendrik Casimir was studying the behavior of the quantum vacuum. We often think of a vacuum as nothing, but quantum field theory tells us it is actually a seething ocean of activity where virtual particles constantly pop into existence and annihilate in the blink of an eye. Casimir predicted that if you took two uncharged, perfectly flat metal plates and placed them incredibly close together, less than the width of a human hair, something strange would happen. Because the plates are so close, they act as a filter for the quantum sea. Only virtual particles with very short wavelengths can fit in the tiny gap between the plates, while virtual particles of all sizes can exist on the outside. This creates an imbalance. There are more particles pushing from the outside than from the inside, creating a net force that pulls the plates together. This is the Casimir effect, and in 1997 it was finally measured with absolute precision in a lab. What makes this relevant to the stars is the energy density between those plates. Because the waves of the quantum vacuum are suppressed in the gap, the energy density there is actually lower than the energy of empty space. By definition, this means the region between those plates has genuine, measurable negative energy density. This was the holy grail for warp drive theorists. The Casimir effect provides the only confirmed real-world evidence that nature does not forbid negative energy. It proves that the impossible fuel source Alcubierre's drive requires isn't just a fantasy, it exists in laboratories right now. But, as with everything in the hunt for FTL travel, there was a sobering reality check. While the Casimir effect is real, it is microscopic. The amount of negative energy produced between two 1-meter plates is roughly 10 to the -7th joules, less energy than it takes for a single mosquito to flap its wings once. The gap between the mosquito wing energy we can create in a lab and the Jupiter-sized energy we need for a starship is a staggering 24 orders of magnitude. It is a factor of a trillion. For decades, this is where the dream stalled. We had a map, Alcubierre's metric, and we had proof that the fuel existed, the Casimir effect, but we had no way to scale it up. We were like ancient humans who had discovered that a single spark could create heat, but were trying to figure out how to use that spark to power a global industrial revolution. The energy crisis was so profound that warp drive research was pushed to the extreme fringes of science, a playground for fringe theorists and science fiction fans. However, in 2011, a physicist at NASA's Johnson Space Center walked into the conversation with a redesign that shocked the specialists. He didn't look for new fuel, he looked for a better engine shape. He proposed that by simply making the walls of the warp bubble thicker and changing the shape of the ship from a sphere to a torus, a donut, the energy bill would undergo one final, miraculous collapse. The requirements didn't just drop, they evaporated. According to his math, we no longer needed a planet. We no longer even needed a mountain. The impossible fuel source had just been reduced to the mass of a single motorcycle. But even as the energy bill plummeted, a new and far more terrifying set of problems was emerging from the equations. Problems that suggested that even if we could build the bubble, we might not survive the trip. Chapter 5. The Optimizers, NASA and the Proton Bubble. By the late 1990s, the dream of the Alcubierre warp drive had hit a wall made of the most unforgiving substance in the universe, pure mathematics. Miguel Alcubierre had opened the door to the stars, but the entry fee his equations demanded was so absurd it bordered on a cosmic joke. To power a single starship, you would need to harvest the mass energy of the entire observable universe and somehow flip it into a negative state. For 5 years, the warp drive was treated as a beautiful but useless ghost, a mathematical proof that travel was possible, but only for a civilization that possessed the power of a god. But in 1999, the first of the optimizers arrived to perform a surgical operation on Einstein's equations. Chris van den Broek, a physicist at the Free University of Brussels, realized that everyone had been looking at the warp bubble the wrong way. We had assumed that if you wanted to fit a 100-meter starship inside a bubble, that bubble had to be at least 100 meters wide on the outside. In our everyday, flat world, this is common sense. A box that looks 1 meter wide on your porch contains exactly 1 meter of space inside. However, general relativity is not common sense, it is geometry. Van den Broek discovered a geometric loophole that felt like it was plucked straight out of a fantasy novel. He proposed a bubble that used extreme curvature to decouple its external size from its internal volume. He theorized a warp bubble that to an outside observer would look no larger than an atomic nucleus, roughly 10 to the -15th meters, or the size of a single proton. To anyone watching from the outside, this proton bubble would be virtually invisible, a microscopic speck racing through the void. But once you stepped across that microscopic threshold, the geometry would bloom. Because space is flexible, the interior of this proton could be engineered to contain a vast flat region of spacetime large enough to hold a full-sized starship and its crew. It is the ultimate magic suitcase, a microscopic exterior hiding a macroscopic interior. By shrinking the mouth of the bubble that actually had to interact with the external universe, Van den Broek achieved a miracle of accounting. He slashed the energy requirement by more than 20 orders of magnitude. The bill for a warp drive journey suddenly dropped from the mass of the entire observable universe to something merely the mass of the planet Jupiter. While a Jupiter-sized fuel tank is still a physical impossibility for 21st century humans, this was the moment the trajectory changed. The warp drive had moved from absolutely impossible to ridiculously difficult. It proved that the energy cost was not a fixed law of nature, but a variable of design. If one clever geometric tweak could shave off 20 zeros from the energy bill, what else was hidden in the math? For the next decade, the field simmered in the background of academia until 2011, when the search for a better engine moved from Belgium to the heart of the American space program. Harold "Sonny" White was not a fringe theorist. He was a physicist at NASA's Johnson Space Center, leading a laboratory with a name that sounded like it belonged in a Ridley Scott film, Eagle Works. Eagle Works was NASA's X-Files division, the Advanced Propulsion Physics Laboratory, where engineers were paid to look at the crazy ideas that might become reality in 100 years. White realized that the previous models were leaking energy because of how they were shaped. In the original Alcubierre design, the transition zone, the wall of the bubble where space shifts from contracted to expanded, was incredibly thin. Imagine trying to bend a thick piece of steel into a 90-degree angle. It takes a massive amount of force to create that sharp, sudden change. White's insight was to thicken the walls. By creating a wider, more gradual boundary, where the geometry shifted slowly, he found he could significantly lower the tension on the fabric of spacetime. Then he changed the ship's profile entirely. Instead of a spherical bubble, White proposed a torus, a giant 3D donut of energy. The starship would sit in the hole of the donut, protected by a ring of warped spacetime that concentrated the gravitational intensity exactly where it was needed and nowhere else. When White plugged this donut-shaped thick-walled geometry into the field equations, the numbers that came back didn't just move the needle, they broke it. The energy requirement for a warp drive didn't just drop, it evaporated. According to White's 2011 presentation at the 100-year Starship Symposium, his redesign dropped the fuel requirement from the mass of Jupiter to approximately 700 kilograms. To put that in perspective, 700 kilograms is roughly the weight of a large motorcycle or a small NASA probe. This was the shot heard round the galaxy for warp drive research. We were no longer talking about harvesting galaxies or stripping gas giants of their mass. We were talking about an amount of exotic matter that could fit inside a medium-sized shipping crate. For the first time in history, the impossible drive looked like it might actually be an engineering problem rather than a theological one. White didn't stop at the math. He wanted to see if he could create a micro-warp in a lab setting. He built the White-Jude warp field interferometer, a device designed to detect the tiniest, most microscopic distortions in spacetime using laser beams. The idea was simple. If you pass a laser through a region of spacetime and that space is even slightly warped by high-voltage capacitors, the light should take a slightly different path, creating an interference pattern. In 2013, rumors began to swirl that Eagle Works had detected an anomalous signal, a hint that they had successfully bent the fabric of space on a subatomic scale. While NASA was quick to clarify that the results were preliminary and likely caused by noise or thermal interference, the damage, or rather the inspiration, was done. The fact that the world's most prestigious space agency was even attempting to measure warp fields gave the entire field a newfound legitimacy. It was no longer career suicide for a graduate student to cite Alcubierre. It was now a cutting-edge frontier of propulsion physics. However, as the optimizers celebrated their victory over the energy bill, a much darker reality was beginning to emerge from the deeper layers of the equations. We had found a way to afford the bubble, but we hadn't yet figured out how to survive it. As the math for superluminal travel became more detailed, physicists realized that a ship moving faster than light wasn't just a vehicle, it was causally isolated from its own front. The optimized bubble had a terrifying flaw: the steering crisis. Because the front of the bubble is moving faster than light, any radio signal or command sent from the pilot's chair can never actually reach the leading edge of the ship. The pilot is like a driver in a car where the steering wheel isn't connected to the wheels and the brakes don't exist. Once you engaged the drive and crossed the light barrier, you were no longer a pilot. You were a passenger on a ballistic projectile that you could not turn and could not stop. And that was just the beginning of the horror. There was still the problem of what happens when that motorcycle mass of energy hits a single grain of space dust at 10 times the speed of light. The optimizers had solved the fuel crisis, but they had accidentally designed the most dangerous weapon in the history of the universe: the genocide beam. Chapter 6: The Warp Drive Genocide Problem. As the scientific community celebrated Harold White's motorcycle-sized energy breakthrough, a new and far more terrifying set of problems began to emerge from the deeper layers of the equations. We had found a way to afford the bubble, but we hadn't yet figured out how to survive it, or how to prevent it from becoming the most devastating weapon in human history. This is the dark side of superluminal travel, a collection of physical hurdles that transform the dream of a sleek starship into the reality of an uncontrollable, planet-killing projectile. To understand the first of these horrors, we must look at what lies between the stars. We often imagine interstellar space as a perfect, pristine vacuum, a total nothingness that offers zero resistance. But space is not empty. It is thinly populated with a ghost-like soup known as the interstellar medium. For every cubic centimeter of void, there is, on average, at least one hydrogen atom, along with helium, stray electrons, cosmic rays, and microscopic grains of cosmic dust. To a ship like Voyager 1, moving at a mere 38,000 miles per hour, this sparse medium is negligible. It's like a light mist through which the probe passes without a scratch. But when you engage a warp drive and accelerate that bubble to 10 times the speed of light, the mist becomes a wall of lead. This is the collision model. As the warp bubble screams through the galaxy, it acts like a colossal, invisible snowplow. Because of the way space is compressed at the leading edge, these interstellar particles do not simply pass through the ship or bounce off the hull. Instead, they become trapped. The warped geometry of the leading edge creates a gravitational reservoir that sweeps up every atom and grain of dust in its path, carrying them along with the ship. As the journey continues across light years of distance, this reservoir grows. These particles aren't just hitching a ride, they are being accelerated by the bubble's propagation to enormous kinetic energies. By the time a warp ship reaches a destination like Proxima Centauri, it is no longer just a vessel, it is carrying a payload of trillions upon trillions of high-energy particles, each one vibrating with the power of a miniature star. This leads us to the terrifying phenomenon known as the death beam, or, more formally, the warp drive genocide problem. The math, worked out by researchers at the University of Sydney, reveals a catastrophic arrival signature. When the pilot finally reaches the target star system and deactivates the warp bubble, the geometry that was holding those particles in check suddenly collapses. In that microsecond, every single atom of hydrogen and every grain of dust the ship snowplowed during its voyage is released at once. They don't just drift away, they blast outward from the ship's position in a tightly focused, hyper-energetic beam. This beam travels in the exact direction the ship was heading, directly at the destination. The energy contained in this blast is equivalent to hundreds of thousands of solar masses worth of kinetic energy concentrated into a narrow cone. If a human crew were to warp into orbit around an inhabited planet, They wouldn't be arriving as explorers. They would be arriving as the trigger for an extinction-level event. The death beam would instantly strip away the planet's atmosphere, scorch its surface down to the bedrock, and potentially vaporize the world entirely. The ship itself would be perfectly safe inside its flat space interior, but the civilization it came to visit would be annihilated before a single hello could be transmitted. As the sources describe it, this is the interstellar equivalent of showing up to a diplomatic first contact meeting with a loaded howitzer pointed directly at the host's face. Any attempt by an alien race to visit Earth using this technology would technically be indistinguishable from a declaration of interstellar war, as the arrival signature itself is a planet-killing weapon. But the horror of the warp drive doesn't end with its potential for accidental genocide. It gets worse when you try to sit in the pilot's chair. This is the steering crisis, a problem so fundamental it makes the navigation of a starship look less like Star Trek and more like firing a blindfolded arrow across a dark room. When a warp bubble exceeds the speed of light, it creates a structure known as a horizon, a boundary in space-time nearly identical to the event horizon of a black hole. This horizon forms because the leading edge of the bubble is moving away from the ship's interior faster than light. This creates a causal disconnect. Imagine you are the pilot. You notice a massive asteroid or a gravitational anomaly directly in your flight path. You reach for the controls to steer the ship, but there is a problem. Your control signals, whether they are electrical impulses, radio waves, or laser commands, all travel at the speed of light. Because the front wall of your bubble is receding faster than light, your signals can never catch up to it. You are causally isolated from the very geometry that is moving your ship. From a navigation standpoint, this is a nightmare. During the voyage, the crew cannot steer, cannot adjust their course, and cannot communicate with the outside universe in the forward direction. The ship simply plows forward on whatever vector it was set to at the moment of launch, unable to respond to changing conditions or avoid obstacles. The most terrifying part of the steering crisis, however, is the braking problem. To stop a warp drive, you must collapse the bubble. But collapsing the bubble requires sending a signal from the ship's interior to the warping region to change its geometry. And as we've established, those signals cannot reach the front wall. This means that once you engage a superluminal warp drive, you cannot stop it from the inside. A superluminal starship is not a ship in the traditional sense. It is a ballistic projectile. You must aim it perfectly, fire it, and then simply wait and hope that your pre-programmed shutdown sequence works, or that there is external infrastructure at the destination to collapse the bubble for you. If the math is off by even a fraction of a percent, you might find yourself screaming past your destination at 10 times light speed, unable to turn, unable to slow down, destined to drift across the intergalactic void until your life support eventually fails. Some theorists have suggested pulsing the drive, switching it on and off at high frequencies to maintain causal contact with the universe, but this introduces severe stability problems. A bubble that keeps collapsing and reforming might emit catastrophic bursts of radiation with every cycle, potentially vaporizing the very crew it is meant to protect. Between the genocide beam that sterilizes your destination and the steering crisis that leaves you a prisoner of your own momentum, the Alcubierre warp drive began to look less like a ticket to the stars and more like a cosmic death trap. We had spent decades trying to solve the energy problem, only to find that the universal speed limit was protected by more than just energy. It was protected by the very laws of cause and effect. But even as these engineering horrors were being mapped out, a new, even more immediate threat was discovered. A threat that didn't just affect the destination or the steering, but the very lives of the crew inside the bubble. If the death beam didn't get you and the steering crisis didn't leave you lost in the void, the vacuum itself was preparing to cook you alive. And that is where the mystery of Hawking radiation turns the warp bubble into a furnace. Chapter 7. The Hawking Radiation, Death Trap. We have spent the last 3 decades of human history obsessed with a single number, the energy bill. We focused on how to shrink the mass of the universe down to the mass of a planet, and eventually to the mass of a motorcycle. We thought that if we could just find the exotic fuel, the stars would be ours for the taking. But as the mathematics of the Alcubierre drive matured, a new and far more intimate horror began to emerge from the equations. It wasn't about whether we could afford the journey, it was about whether the laws of physics would allow a human being to survive a single second inside the bubble. This is the story of how the quantum vacuum, the very fabric of nothingness, turns from a silent partner into a lethal high-energy furnace the moment you cross the light barrier. To understand the death trap, we first have to revisit the geometry of the bubble itself. In Chapter 6, we discussed the steering crisis, the fact that when a ship moves faster than light, it becomes causally disconnected from its own front. This isn't just a navigation problem, it is a structural one. Because the front wall of your warp bubble is receding from you faster than a light signal can travel, you have effectively created a horizon. To anyone standing on the bridge of that ship, the leading edge of the bubble isn't just a wall, it is a functional twin to the event horizon of a black hole. In a black hole, the horizon is the point of no return because space is falling inward faster than light can climb out. In a superluminal warp drive, the horizon is created because the bubble is moving outward faster than light can catch up. It is a boundary in the universe across which no information, no light, and no physical influence can ever pass. But as Stephen Hawking famously proved in 1974, horizons are never truly silent. They are the birthplaces of Hawking radiation. According to quantum field theory, empty space is actually a seething ocean of virtual particle pairs that pop into existence and annihilate each other in the blink of an eye. Normally, these pairs cancel each other out, leaving the vacuum at a net zero energy. But when you introduce a horizon, the rules of the game change. Near the boundary of your warp bubble, these virtual pairs are torn apart by the extreme geometry. One particle falls forward into the void the bubble is consuming, while its twin falls backward into the ship's interior. To the crew inside, it would look as if the vacuum itself has begun to bleed. This brings us to the catastrophic findings of a 2009 study by physicists at the University of Sydney. They took Hawking's original math, which was designed for stars, and applied it to the microscopic scale of a human starship. In the world of black holes, size matters in a very counterintuitive way. A massive black hole, like the one at the center of our galaxy, is actually quite cold, emitting radiation at temperatures so low they are almost undetectable. But as a horizon gets smaller, the radiation temperature explodes exponentially. A warp bubble is tiny compared to a star. Because its radius of curvature is measured in feet rather than miles, the Hawking temperature at the leading edge of a superluminal ship would reach millions of Kelvin. This is hotter than the surface of the sun. The moment you engage your warp drive and exceed the speed of light, the interior of your ship would be instantly bathed in a concentrated stream of X-rays and gamma rays. You wouldn't just feel a warm glow, you and your entire ship would be vaporized in a fraction of a second. The Sydney researchers were blunt. There is no shielding that can save you. You cannot line your hull with lead or water to stop this radiation, because the radiation is not coming from outside the ship. It is being generated by the spacetime geometry itself, right between the crew and the bubble's wall. To place shielding between yourself and the source would require disrupting the very warp field that is carrying you, causing the drive to collapse. We had spent years dreaming of faster-than-light travel, only to find that the universe has a built-in incineration protocol for anything that tries to violate its causal speed limit. This realization transformed the entire field of warp research. It forced us to look at the subliminal loophole not as a failure of ambition, but as a sanctuary for survival. This is the subliminal solution. In 2024, when the Jared Fuchs paper from Applied Physics introduced a warp drive that used ordinary matter, the headlines were quick to point out that it couldn't go faster than light. For many, this felt like a letdown, but for those who understood the Hawking radiation problem, it was a breakthrough. By staying subliminal, even if you are traveling at 99.9% the speed of light, you never create a true horizon. Without a horizon, the quantum vacuum remains stable. There is no Hawking radiation, no death beam accumulation, and no steering crisis. Suddenly, the boring version of the warp drive, the one that follows Einstein's rules, became the only version that doesn't result in an immediate crew fatality. This is the subliminal revolution. While we may not reach Proxima Centauri in a weekend, a subliminal warp ship would allow us to cross our own solar system with a level of ease that borders on the miraculous. Imagine a journey to Mars. Today, that trip requires 6 to 9 months of drifting through a zero-gravity void, subject to bone loss and radiation. Because we are limited by the G-forces our bodies can withstand, we have to coast most of the way. But a subliminal warp bubble allows for acceleration without inertial forces. You could accelerate to 90% of light speed in a matter of hours, and the crew inside would feel as if they were sitting on a park bench on a still afternoon. You could reach Mars in hours and Jupiter in weeks, arriving fresh and healthy, all because you had the wisdom to stay just below the threshold where the universe turns into a furnace. The Hawking radiation death trap teaches us a profound lesson about the architecture of reality. The light barrier is not just a speed limit on a signpost, it is a safety railing. It protects the causality of the universe and, as it turns out, protects the lives of any would-be explorers. By moving from the fantasy of superluminal travel to the engineering of subliminal warp, we have traded an impossible dream of godlike speed for a real-world path to becoming a multi-planetary species. But even if we accept the subliminal limit, one massive question remains. We have a design that uses ordinary matter. We have a design that won't cook the crew. But do we have a way to detect if someone else has already figured this out? If alien warp drives are crossing the galaxy right now, they would be leaving a footprint, a signature in the very fabric of space that we are finally learning how to hear. And that is where our hunt for alien warp signatures begins. Chapter 8. The 20-24. Breakthrough Warp Without Magic. For 30 years, the Alcubierre's drive existed in a state of scientific purgatory. It was a beautiful mathematical proof, but one that required a deal with the devil. To reach the stars, we had to find a fuel source that the universe seemingly refused to provide. For decades, the magic of exotic matter, that hypothetical substance with negative energy density, was the only way the equations would balance. This created a fundamental divide in the physics community. Most mainstream scientists viewed warp drive as a fascinating mathematical curiosity with zero connection to engineering reality. But in the early 2020s, the conversation shifted from the dusty chalkboards of traditional academia to a sleek, modern office building in the heart of Midtown Manhattan. Inside 477 Madison Avenue, a private research organization called Applied Physics began a quiet revolution. This wasn't a government laboratory or a university department subject to the slow grind of public grants. It was a team of engineers and physicists, thinkers like Gianni Martire and Jared Fuchs, who decided to treat warp drive not as a philosophical puzzle, but as a systematic engineering problem that could be solved. The team at Applied Physics operated under a simple but radical mission: treat the warp drive as a physical object. In 2021, they released a landmark framework that organized every theoretical warp drive ever proposed into a clear taxonomy. They realized that every warp drive, regardless of its shape, consisted of three distinct regions: a flat region far from the ship, a flat passenger region at the center where the crew sits, and a warping shell in between that does the heavy lifting of bending space. By mapping the solution space of these shells, they began to hunt for a design that didn't require the magic of negative energy. On April 29, 2024, they found it. In the journal Classical and Quantum Gravity, the Applied Physics team, led by Jared Fuchs, published a paper titled Constant Velocity Physical Warp Drive Solution. How this was the moment the cosmic firewall finally showed a crack that didn't require a miracle to exploit. For the first time in history, the team presented a warp drive solution that satisfied all of the classical energy conditions. To understand the weight of that sentence, you have to understand the energy conditions, the laws of the universe that act as a cosmic filter for what is and isn't physically possible. For 30 years, every FTL design violated these conditions. They required unphysical energy that didn't exist in our material inventory. But the 2024 Fuchs design violated none of them. It required no negative energy, no exotic matter, and no anti-gravity fuel. This is what researchers call the clean solution. Instead of relying on exotic matter to push space apart, the Fuchs design uses ordinary positive energy matter, the kind of stuff we can actually touch and measure, like protons and electrons, arranged in a sophisticated, stable shell with a specific density distribution. The secret sauce isn't a new kind of matter, but a mathematical feature called a shift vector distribution. This distribution describes a flow pattern of space that mimics the Alcubierre geometry, compressing space in front and expanding it behind, but doing so using the gravitational interaction of ordinary matter. So for the first time since 1994, we had a warp drive design that didn't require anything the universe refused to provide, as it moved the project out of the realm of fantasy and into the realm of extraordinarily difficult engineering. But how did a small team in New York manage to find a solution that had eluded the world's greatest minds for 3 decades? They didn't do it with just pen and paper. They did it by building a new kind of telescope for the mathematics of spacetime. They created a software package called Warp Factory. Before Warp Factory, evaluating a new warp drive design was a brutal, labor-intensive process. A researcher would write down a complex mathematical description of a bubble and then spend months manually calculating whether the energy conditions held or if the ship would be crushed by tidal forces. Mistakes were common, and comparing different designs was nearly impossible because every paper used different notations. Warp Factory changed the game. Written in MATLAB, it is a publicly available tool that allows any physicist on Earth to input a metric, a recipe for warped space, and instantly see a high-definition visualization of its properties. The software uses a simple, intuitive color coding system to judge a design's viability. In the Warp Factory interface, blue represents positive energy density, the clean, ordinary matter we know how to use. Red represents a violation of energy conditions, the magic, exotic matter that we don't have. When you run the original 1994 Alcubierre metric through the software, the screen is flooded with red. But when the 2024 Fuchs metric is plugged into the system, the visualization is entirely blue. It is a physical solution in every sense of the word, confirmed by a rigorous numerical simulation that checks every tensor and every curvature scalar against the known laws of physics. The 2024 breakthrough wasn't just a win for Jared Fuchs, it was a win for the global research community. Because applied physics released Warp Factory under an open license, research groups from Germany to Japan are now using it to scan thousands of candidate designs, hunting for the next refinement. They are moving from a world where we hoped for a miracle to a world where we are tuning a machine ink. However, as the blue visualization of the Fuchs bubble flickered to life on the monitors at Applied Physics, it carried with it a sobering realization. While the team had successfully removed the magic fuel requirement, they had encountered a different kind of wall. In interviews and press releases, Fuchs was careful to emphasize a caveat that many headlines chose to ignore. The 2024 solution is explicitly subluminal. This clean warp drive, built from the matter of our daily lives, moves at a constant velocity that is less than the speed of light. It turns out that the moment you try to push the blue ordinary matter shell past the light barrier, the equations start demanding red exotic matter again. Crossing the light barrier creates the horizons we discussed in previous chapters, and horizons, by their very nature, seem to act as a causal guardrail that ordinary matter alone cannot cross. But for some this felt like a step backward. Why build a warp drive that can't go faster than light? If we are still limited to sub-light speeds, aren't we still trapped in that 70,000-year prison? The answer, as we are about to see in Chapter 9, is a resounding no. By accepting the subluminal limit and embracing the Fuchs breakthrough, we haven't lost the stars. We have gained the solar system. We have found a way to bridge the gap between impossible fantasy and a real-world path to becoming a multi-planetary species. The 2024 breakthrough didn't give us Star Trek-style travel today, but it gave us the first valid engineering roadmap for a propulsion system that could revolutionize the 21st century. 8. We have found the door. It isn't magic, and it doesn't require unobtainium. It just requires a level of engineering that humanity is, for the first time, beginning to grasp. Chapter 9. The Subluminal Revolution. In the world of viral headlines and social media hype, the 2024 Jared Fuchs paper was often presented as the moment Star Trek became real. But if we are going to be elite chroniclers of this journey, we have to start with a dose of cold, scientific honesty. The 2024 breakthrough is explicitly subluminal. This is the catch that many casual observers missed. While the team at Applied Physics successfully removed the requirement for magic, exotic matter, they discovered that the light barrier is a far more stubborn guardrail than we ever imagined. The moment you attempt to push that clean, ordinary matter shell past 100% of light speed, the equations immediately demand the return of red negative energy to stabilize the resulting horizons. For many, this felt like a catastrophic retreat, a surrender to the 70,000-year prison we discussed in Chapter 1. But for the engineers and mission planners looking at the next 2 centuries of human expansion, this subluminal limitation isn't a failure, it is a foundational revolution. By accepting that we are staying below the light barrier, we are trading a lethal, impossible fantasy for a viable, survivable engineering roadmap. We are moving away from a drive that vaporizes its crew with Hawking radiation and toward a drive that could turn the entire solar system into a local neighborhood. To understand why a slower-than-light warp drive is still the holy grail of propulsion, we have to look at the solar system prize. Right now, our missions to Mars are dictated by the brutal ballet of orbital mechanics. We have to wait for launch windows that only open every 26 months, we have to spend 6 to 9 months drifting through a radioactive void, and we have to subject our astronauts to the debilitating effects of zero-gravity bone loss because our chemical rockets simply cannot carry enough fuel to provide sustained thrust. even the most powerful rockets today, are brute force machines. They accelerate the crew at bone-crushing g-forces for a few minutes and then leave them to coast for months. A subluminal warp bubble changes the very definition of transit. Because the ship inside the bubble is technically stationary within its own flat space pocket, it is completely immune to the laws of inertia. Imagine a starship departing from Earth orbit. In a conventional craft, if you tried to accelerate to 90% of the speed of light in a matter of seconds, the crew would be instantly liquefied against the back wall by thousands of Gs of force. But in a warp ship, you could engage the drive and accelerate to 90% light speed instantly, and the passengers would feel absolutely nothing. They could be standing on the bridge holding a cup of tea as the Earth recedes into a tiny blue marble behind them. They would feel as though they were sitting on a park bench on a still afternoon, even as they cover millions of miles every minute. With this inertialess travel, the distances of the solar system essentially collapse. A journey to Mars would take mere hours. A trip to the moons of Jupiter would be measured in weeks. We would no longer be waiting for launch windows or transfer orbits. We would simply point the ship at our destination and go. This capability would transform humanity from a single-planet species into a true multiplanetary civilization. It would mean that a rescue mission to a lunar base or a delivery of supplies to a Martian colony would be as routine as a transatlantic flight is today. However, even with the magic fuel of exotic matter removed from the equation, we are still standing before a monumental engineering wall. The 2024 breakthrough gave us the math, but it also highlighted a massive materials science gap. To hold a warp bubble together, the matter shell must possess a density and structural integrity that defies every material currently known to man. When you warp spacetime, you are dealing with forces of unimaginable magnitude. Current high-strength materials like carbon fiber composites or advanced steel alloys are designed to handle pressures in the range of a few gigapascals. A warp shell, however, requires a material that can withstand stresses thousands of times higher than steel without deforming or shattering. We are talking about materials that can maintain a precise geometric configuration while under the crushing weight of the universe's own geometry. This is the roadmap for the next century of research. We are looking at the development of engineered quantum materials, metallic hydrogen, or bulk carbon nanotubes that could theoretically serve as the structural frame for a warp shell. But we aren't just building a faster rocket, we are learning how to build a machine out of gravity itself. This is a centuries-long engineering goal, a multi-generational project that requires us to master energy production on a scale humanity has never attempted. To power even a subliminal bubble, we would need energy inputs comparable to a significant fraction of the total power generation on Earth, sustained for the entire duration of the trip. We would need a civilization powered by mature fusion reactors or matter-antimatter annihilation just to turn the key in the ignition. So, where does that leave us? It leaves us with a physical warp drive that is finally consistent with the laws of nature, but remains just out of reach of our current hands. We have moved from the era of impossible dreams to the era of patient refinement. We are like the early 19th century dreamers who looked at the first steam engines and imagined a world connected by iron rails, or the pioneers who looked at the first gliders and saw a path to the moon. They didn't have the materials or the fuel to make it happen in their lifetime, but the math told them they were right. The subliminal revolution is the moment we stopped trying to cheat the universe and started learning how to work within its rules. By staying below the light barrier, we avoid the lethal radiation of the Hawking trap. We avoid the steering crisis of being causally disconnected from our own ship. And we avoid the genocide beam that would sterilize our destination upon arrival. We have found a clean and safe path to the stars. The 25 trillion-mile gap to Proxima Centauri is still there, and at sublight speeds it will still take us years to cross. But for the first time in history, that journey is no longer a suicide mission. It is an engineering challenge, a long, difficult, and expensive one. But it is a challenge that humanity has finally proven is mathematically possible. But while we are laboring in our labs to build the first microscopic warp shells, we have to wonder, if the math is this clear, has someone else already built one? If there are alien civilizations out there, they aren't just sending radio signals, they are warping the fabric of the galaxy, and we are finally learning how to listen for the ripples they leave behind. Chapter 10. Hunting Alien Signatures. For over 60 years, the search for extraterrestrial intelligence, SETI, has operated on a single, silent hope that somewhere out there, among the billions of stars in the Milky Way, someone is broadcasting a radio signal that we are clever enough to catch. We have built massive dishes, scanned millions of frequencies, and listened for a hello in the static of the cosmos. But the silence has been absolute. For decades, we assumed this meant we were alone, but the mathematics of the warp drive suggests a far more tantalizing possibility. It suggests that we may simply be looking at the wrong channel. If an advanced civilization has already mastered the ability to bend space-time, they wouldn't necessarily be leaking radio waves. Instead, they would be leaving ripples in the very fabric of the universe itself. Ripples that we are finally learning how to hear. This search shifted into high gear on April 29, 2024, when a team of physicists led by Katie Clough at Queen Mary, University of London, published a paper titled What No One Has Seen Before: Gravitational Waveforms from Warp Drive Collapse. For the first time, researchers didn't ask how to build a warp drive, but what happens when one breaks. They used numerical relativity simulations, the same supercomputing power used to model the collision of black holes, to see what the death rattle of a warp drive would look like. The result was a specific, unique footprint unlike anything astronomers have ever seen. When a warp bubble fails, it doesn't just disappear. The warped geometry of spacetime undergoes a violent, catastrophic reconfiguration as it relaxes back to a flat state. This release of stored energy sends out a burst of high-frequency gravitational waves. The waveform has a distinct signature, a brief, intense burst of oscillations followed by a ring down, a decaying pattern as the universe settles. This is where the search gets difficult. Current observatories like LIGO are ears tuned to the low-frequency rumble of massive black hole mergers peaking around 100 Hz. But the collapse of a kilometer-scale warp drive would happen at a much faster tempo, approximately 300 kHz. To LIGO, an alien warp drive failing in our own galactic backyard would be completely silent. However, the 2024 paper has given us a template to build new ears. Proposals for next-generation detectors using superconducting resonators or microwave cavity arrays could specifically target these frequencies. We aren't just looking for a signal anymore. We are looking for the accidental clank of alien machinery failing across the void. But what if their technology doesn't fail? This leads us to the concept of Raumkraft wakes. Any object moving through spacetime, especially one that aggressively contracts and expands space around itself, must produce a gravitational disturbance. In the same way a boat leaves a wake in a lake, a warp bubble leaves a gravitational trail as it carries its contents across the galaxy. The beauty of searching for these wakes is that they are immune to the barriers that frustrate radio telescopes. Gravitational waves are not blocked by the thick clouds of interstellar dust that obscure the center of our galaxy. They don't require the aliens to be pointing a transmitter at us, and they don't suffer from frequency mismatch problems. A gravitational signal from the other side of the Milky Way arrives at Earth essentially unchanged, carrying the raw data of the propulsion system that created it. In the 2030s, the launch of LISA, the Laser Interferometer Space Antenna, a triangle of laser-linked spacecraft, will open a new window into these lower-frequency propulsion wakes. For the first time, we could detect the bulk acceleration of a massive alien matter shell as it speeds up to 90% of light speed. We might find evidence of Ramacraft long before we ever hear a radio broadcast, turning our search for ET from a hunt for messages into a hunt for interstellar traffic. However, as we peer into the darkness for these ripples, we must remember the ethical horror of the technology we are looking for, the genocide beam we discussed in Chapter 6. If we do detect a warp signature heading toward our solar system, we face a terrifying diplomatic paradox. Because a superluminal bubble is indistinguishable from a planet-killing beam of high-energy radiation, we would have no way to know if we were being visited by a peaceful ambassador or targeted by a declaration of interstellar war. The arrival signature of a warp ship is a loaded weapon pointed at the heart of the host star. This suggests that any truly advanced civilization would likely remain subluminal, arriving slowly and safely to avoid the accidental annihilation of their neighbors. As we conclude this mission briefing, we have to be honest about where we stand. We have not yet broken the light barrier. We do not have 700 kilograms of exotic matter tucked away in a lab. We are still, for all intents and purposes, trapped in our 70,000-year prison, looking at a 25 trillion-mile gap that our current rockets cannot cross. But something fundamental has shifted since the 1990s. Warp drive is no longer just a science fiction trope used to move a plot forward. It has become a valid, rigorous solution to Einstein's field equations. We have moved from the fantasy of the Alcubierre drive to the engineering of the 2024 Fuchs physical warp drive. We have identified the Hawking radiation death trap and realized that the light barrier isn't just a limit, it's a safety railing that protects the causality of our universe. The transition from the 20th to the 21st century has turned the warp drive from a dream into a centuries-long engineering goal. We are in the steam engine phase of interstellar travel, the phase where the math says yes, even if the materials say not yet. We need materials thousands of times stronger than steel and energy outputs that rival the total production of our entire planet. These are not impossibilities, they are milestones. We are a species that has only possessed the concept of gravity for 400 years, yet we have already photographed the event horizon of a black hole and detected the ripples of merging stars billions of light years away. The distance to Proxima Centauri is 25 trillion miles, a number that seems designed to break our spirit. But as we refine our equations, build our warp factories, and tune our gravitational detectors, we are proving that we are no longer content to be prisoners of the void. The mission to the stars is no longer a question of if, but a question of patience, refinement, and time. One equation at a time, one simulation at a time, we are learning how to bend the universe to our will. Somewhere in a future we cannot yet see, the first warp bubble will learn how to expand and contract, and humanity will finally step out of its cradle and into the local stellar neighborhood. The navigation console is open. The math is written. Now the real work begins.